Hi, today we are going to learn about estimation of parameters of Michaelis-mentate equation. What are those parameters? Those parameters are Km, that is Michaelis-mentate constant, and Vmax, that is maximum concentration at which the reaction is going on, maximum velocity at which reaction is going on. That what we are going to determine in the Michaelis-mentate equation. For that, you need to consider a reaction which is capacity limited, or any process which is capacity limited, like the processes we have metabolism, renal tubular secretion, or biliary excretion, or anything which is capacity limited. To know what is this Michaelis-mentate equation and what are its basics, you need to go and check my video on the basics of Michaelis-mentate equation. I will put that in the iCard, or I will give in the description. You can go and check that details of Michaelis-mentate equation for basics. So we directly move on to the estimation of parameters of Michaelis-mentate equation. In the estimation of parameters of Michaelis-mentate equation, we need to consider one process, consider any one process of drug elimination or drug absorption, anything. Consider a process which is following one compartment model. So we need to consider a process following one compartment model. So after injecting the drug should follow one compartment model, and its elimination should involve only single capacity limited process. What do you mean by single capacity limited process? We don't, during elimination, if it is eliminating through active process, not passive, active process, in that active process, its elimination, the active thing which is involved in the elimination should be single, not two or three process by active elimination. It's only eliminated by single active process. That's what the requirement is. So I repeat, the requirement is drug should follow one compartment model, and the elimination should have only one active capacity limited process. So we are going to determine Km and Vmax from the plasma drug concentration. So from the plasma drug concentration, we are going to determine the Km and Vmax after collecting the plasma drug concentration from IV bolus administration. Means what? I am giving IV bolus administration of a drug is following one compartment, the elimination is single capacity limited, and I will collect the data from the plasma drug concentration. From that data we can find the parameters of Km and Vmax. That is your Michaelis-mentate parameters, Km and Vmax. So if we see the Michaelis-mentate equation, this is what the Michaelis-mentate equation is: minus dC by dt is equal to Vmax C by Km plus C. From here we'll try to see how to measure the Km and Vmax value. So I have already written this here. We'll try to see this. Yeah, see here. So our equation is, this is our equation. Yeah. So this is our equation, Michaelis-mentate equation. So in this equation we want to convert, because we want to measure the values of parameters, we need to convert that equation in some format. So for that conversion, what we need to do is integrate this equation. This equation should be the equation should be integrated and convert to log base 10. So you need to integrate this equation. This above equation should be integrated and it should be converted into log base 10 format. If you do that, you will be end up with the following equation. This is a equation with which you are end up with. So you will be end up with the following equation. This is the equation. So if you integrate the Michaelis-mentate equation and convert it into log base 10, you will get this equation. How we got that? You should know what is the integration and how to convert that equation into log base 10. So it is pure max. I am not going into detail of that. We will try to see this. Okay. After integrating and converting into log base 10, you will be end up with this equation. We can draw plot for this equation. If you draw the plot for this equation, you need to take this as for any plot we should have y is equal to mx plus c. Take this as y axis. Okay. Take this whole thing as m and take t as x axis. So if I draw the plot will look like this. See here. So I have taken log C on y-axis. This is the log C that I have taken on y-axis. I have taken time on x-axis because this process is a mixed process. Michaelis-mentate equation process is a mixed process. It is giving me not straight line. It is initially giving me curve line. Then after some time it is giving me straight line. So I will try to mention here. So initially from here to here it is curve, and from here to here it is straight. This is curve and this is straight. So we have two lines here, one curve line and another one straight line. Now we'll see what are the things we need to get from this curve line and the straight line. We need to measure Km and Vmax values from this thing. If we extrapolate whatever the straight line is there, if you extrapolate this straight line will touch to the y-axis somewhere. You should extrapolate the straight line. So if you extrapolate the straight line, this straight line will touch at the y-axis somewhere. That is called as your, see, wherever this line is, this normal line is touching, that is your log C. That normal line is touching. Wherever the extrapolated line is touching, that we call it as log C naught extrapolated. For the extrapolated, we represent the arrow mark, back arrow mark. If I represent the back arrow mark, it indicates we are extrapolating the line. So wherever the normal line meets the y-axis, that is log C naught. Wherever the extrapolated line meets the y-axis, that is log C naught extrapolated. Okay. For this straight line, we have another equation, that is this equation. So whatever the equation is there, this equation represents the straight line. So for one graph, we have two equations. One is the normal equation, above equation, this one, equation 1. Another is equation 2. This one is equation 2. Equation 2 is for extrapolated line. Equation 1 is for normal line. Okay. Now we'll see what to get here. So if you take, you can take anything here. If you take extrapolated line or straight line in the curve line, if you take straight line, the slope will give you Vmax by 2.303 km, and also the slope of extrapolated line will give you this one, Vmax by 2.303 km. In both the case, see this one, in both the case we get the slope as Vmax by 2.303. Now I want to find the value of Vmax and Km. In this equation we can find only the value of one thing. Okay, see, if I take slope is equal to Vmax by 2.303 km. So if I get slope value something like let's say I am getting slope value as x, if I multiply that also, in this case we have two unknown values. The two unknown values are Vmax and Km. I need to find we have two unknown values. So for that I need to find one value at least. If I find one value and substitute in this equation, slope equation, I will get another value. So for that what we have to do is, at low concentration, if you conduct the experiment at low concentration, whatever the two equations we got, see here we have equation 1, this is the equation 1, this one is equation 1, this one is equation 2. Whatever the two equations we have, but both are equal if you conduct the experiment at low concentration. So at low concentration, equation 1 and 2 are identical. Why I am doing this? To know one value, that is Km. So identical. I will write the equation here. So second equation is been written here, first equation is been written here. So whatever the common things are there, we are going to cancel these common things here. Okay, then we will be left with this one. See, log C naught back extrapolated is equal to C naught plus C naught by C naught minus C by 2.303 km. Okay, if you rearrange this equation, send this C naught this side, you will get log C naught back extrapolated minus C naught, and rest is the equation. So log A minus log B is log A by B. So that's what we get, log A by B is equal to the rest equation. If you substitute the value of back extrapolated C naught and normal C naught, from where you will get this value, normal C naught you are going to get from here, back extrapolated C naught we are going to get from the extrapolated line. So if you substitute those two values in this equation, you can find Km value in this equation. Now because you obtain the Km value, substitute this Km value in the slope equation. So in this equation, what we have, we know Km, we know 2.393. Multiply 2.393 and Km with the slope value. Whatever the value of slope you got, slope multiplied by 2.393 into Km will give you Vmax value. So this is how you find out Km and Vmax value from this method. Alternate method, some other method is there through which you can find out the Km and Vmax value. The alternate approach method. We'll see what is that method. So determining the rate change of plasma concentration at different time interval. Determining the rate change of plasma concentration at different time interval, we can also determine the Km and Vmax value. How to do that? Use reciprocal equation. Whatever the equation you have for Michaelis-mentate equation, just inverse it. If you inverse that equation, you need to use reciprocal equation of Michaelis-mentate equation. What is that reciprocal equation? This is the reciprocal equation of Michaelis-mentate equation. Now how we got that equation? See here. Step 1, this is the equation of Michaelis-mentate. If you reciprocate, just divide it by 1 by dc by dt. This Km plus C will go up, Km by Vmax C. This Vmax C will be for both, plus C by Vmax C. So Cc will get cancelled. The remaining is 1 by dc by dt into Km by Vmax C plus 1 by Vmax. The reciprocal equation of Michaelis-mentate equation. In this, what is, you can ask me, sir, you are writing here C and you are written here Cm. Cm means mid plasma concentration. If you are carrying out any experiment, whatever the concentration at mid time, so this is called Cm. Cm is mid plasma concentration. Okay. So now we got the reciprocal equation. Now draw a plot for reciprocal equation. Take dc by dt on y-axis. Here we have plot here. dc by dt on y-axis and 1 by Cm. See whatever here is 1 by Cm. This 1 by Cm is taken on. This is on x-axis. This one is on y-axis. So 1 by Cm on y-axis. We'll get, because we have positive here, we'll get straight line, positive straight line. This positive straight line, the slope will give you Km by Vmax. See whatever the Km by Vmax is there, that what is your slope, and the intersect point will give you what? 1 by Vmax. The intersect point will give you 1 by Vmax. So you know 1 by Vmax. Find out what is the value of Vmax. What is the intersect is equal to 1 by Vmax. So Vmax is equal to 1 by intersect value. You know the Vmax value. Substitute that Vmax value in the slope. So what is the slope? Km by Vmax. Slope is your Km by Vmax. So substitute the value of Vmax in the slope. So slope multiplied by Vmax value will give you Km directly. So in this method also you can determine the Km and Vmax values. This particular graph we call it as Line-weaver-Burk plot. Okay, we call it as Line-weaver-Burk plot. So reciprocal of your Michaelis-mentate equation plot, whatever we got there, we call it as Line-weaver-Burk plot. Okay, so disadvantage here. What is the disadvantage of Line-weaver-Burk plot? Is this plot is very scattered. See, scattered means what? See, you get the values like this, scattered values. So you get the values all around. We don't want that. We want the values to be linear. If at all they scatter also, some value should be linear like this. So if you have linear values, you can plot the graph. I want linear values. For that, we use more reliable plots. Instead of using Line-weaver-Burk plot, which is the reciprocal plot, reciprocal equation plot of Michaelis-mentate. What is Line-weaver-Burk plot? It is the reciprocal equation plot of Michaelis-mentate equation. Okay, we reciprocate the Michaelis-mentate equation and we plot the graph. Now, because we are getting scattered lines in the Line-weaver-Burk plot, to avoid that scattering, we want linear lines to appear. For that, we will go for the reliable plots. What are those reliable for? For uniform scattering, we want reliable. For this type of scattering, we want reliable plots. What are those plots? One of the plot is Hans-Wolff plot. What is Hans-Wolff plot? See, this is the equation for Hans-Wolff plot. You can ask me, sir, how we got this equation? This is the equation for plot which I am going to draw about. How we got this equation? We got this equation by multiplying the reciprocal equation of Michaelis-mentate with Cm. See here, Cm is there. This equation is reciprocal of Michaelis-mentate equation. Multiply that reciprocal equation with Cm. If you multiply the reciprocal equation with Cm, see, we got same equation. Okay, Hans-Wolff plot is brought by multiplying the reciprocal equation of Michaelis-mentate equation. What is the reciprocal equation? This is the reciprocal. This particular thing is reciprocal equation. This equation you should multiply with Cm. You will get Hans-Wolff plot. So how to draw the plot? You need to plot the graph by taking this particular thing on y-axis. I will take this on y-axis. So I have taken here. We taken this on y-axis, and we are taking Cm, which is there here. See here, whatever Cm is there, we should take it on x-axis because we have positive slope, hence we got positive graph. So what the slope will give here? If this is x, what is the value? Y is equal to mx plus c. What are present beside x is called m. What is m here? 1 by Vmax. So slope is 1 by Vmax. M is slope. Slope is your 1 by Vmax, and the intersect point is Km by Vmax. This is c. This is 1 by Vmax is m. This is x. Okay. So Km by Vmax is intersect point. So you know from the slope you will find Vmax value. Substitute that Vmax value in the slope. What is your slope? Slope is equal to Km by Vmax. So Vmax multiplied by slope will give you Km. In this method also you can find out the parameters of Michaelis-mentate equation. Why we go to this method? Because the previous method is giving me scattered thing. We want a linear graph to be plotted. Hence we go for the Hans-Wolff plot. Next plot is Woolf-Augustinsson Hofstee plot. Woolf-Augustinsson Hofstee plot. So how we get this plot? By this equation. How we got this equation? I tried to derive it. I didn't find that. If any student is going to find that derivation for this equation, please let me know this. Okay. So same equation is modified here. If you modify Michaelis-mentate equation, you will get this equation. We need to plot the graph for dc by dt. Take this as y-axis, and whatever this one is there, this thing is taken on x-axis. So this will be your m and this will be your c. What is m? M is your minus km. Minus km is m. So from the slope you can find out km value, and from the intercept you can find out Vmax value. Simple things. So that what is Woolf-Augustinsson Hofstee plot. So what is this plot? This plot, why we are going for this plot? Because the previous one I am not getting, the reciprocal equation is giving scattered points. I want linear points to plot the graph. For that we go for the next two graphs. Okay, among them one graph is Woolf-Augustinsson Hofstee plot. This plot is brought into life by modifying the equation of Michaelis-mentate and plotting the graph for that modified equation. You plot the graph for the modified equation. Okay. Next, we can also find out, these all are one method. We can also find out the above methods are valid for one compartment model. Okay, IV infusion. Now, we can also find Km and Vmax value by steady state. So how to find out Km and Vmax value by steady state? We can also find that by steady state equation. We'll see what is that. So in the steady state, dr. In the steady state, your dr is dosing rate. What is dosing rate? Okay, dosing rate is equal to steady state multiplied by clearance. We'll see whether it is correct or not. What do you mean by dosing rate? How many grams of drug is been injected per given time. So gram per second is the units for dosing rate. We'll see with this whether the whatever the equation we have here it is correct or not. So the dosing rate is gram per second, and concentration is gram per ml. Clearance is ml per second. Cancel ml and ml here. You will be end up with only gram per second. So this equation is correct. You can check whether the equation is correct or not by this unit tracking method. You can track the units and you can find out whether the equation is correct or not. So this equation is correct. Next, at steady state. Okay, what do you mean by steady state? Okay, at steady state dosing rate. So whatever you are injecting is equal to whatever going out. So how much you are injecting should be equal to whatever the amount going out. So if I inject 10 molecules per second, 10 molecules per second should go out. Then only the plasma drug concentration will remain steady. If the decline in the, whatever we are saying, the decline in the drug means whatever the drug is removed from the body, if decline in the drug concentration is single capacity limited process. Let's say we have metabolism. Your drug is metabolizing by single capacity limited process. That is, one enzyme is only metabolizing the drug. In that case, what we can do? We can determine the value of Vmax and Km also through steady state diffusion. We'll try to see this. Then what we have to do here is take this Michaelis-mentate equation. This is a Michaelis-mentate equation. dC by dt is equal to Vmax C by Cm Km plus C. So instead of C, you take steady state concentration CSS. Instead of dC by dt, you can directly take, you can directly take dosing rate. So whatever the thing is there, it will remain same. Only thing you have to substitute here is, instead of C, you take CSS, because we are measuring the values of Km and Vmax in steady states, hence we should represent as CSS. Okay. Now from this equation we can determine the Km and Vmax value by three methods. One method is again Line-weaver-Burk plot. I already said you what is Line-weaver-Burk plot. It is the inverse plot drawn by taking inverse of Michaelis-mentate equation. To draw Line-weaver-Burk plot, you need to inverse the Michaelis-mentate equation. In this case, we are going to inverse this equation. Inverse the equation. I will tell you that in the coming session. Okay, then direct linear plot, and the third method is graphical method. So by using only this equation, we can determine the Vmax and Km value by three methods. First method is Line-weaver-Burk plot. I told you Line-weaver-Burk plot is drawn by taking the inverse of this equation. This is the Michaelis-mentate equation modified for the dosing rate according to your steady state concentration. Okay, inverse this equation. If you inverse this equation, you will be left out with this equation. After cancelling the common terms, we will be left out with this equation. Now draw the plot. Take 1 by dr on y-axis, 1 by CSS. This is 1 by CSS and x-axis. Again, we will be left out with slope will be your Km by Vmax. This is your slope, Km by Vmax, and the intersect point is Vmax. We know what is intersect value. We know from the intersect value we can find out what is Vmax value. Substitute that Vmax value in the slope, that is Km by Vmax. So slope is equal to Km by Vmax. Multiply this Vmax with the slope value, you will get Km value. So Line-weaver-Burk plot coming for two times here, without steady state, and with steady state also. Next, the only thing here is, instead of writing dC by dt, we are taking dosing rate. That's all. Okay, because we are taking for steady state, we need to write, instead of dC by dt, we need to write dosing rate. Next is direct linear plot. To plot this graph, you need to conduct the experiment in two doses. So conduct the experiment, same steady state, achieve steady state in that specimen by inserting two different doses. So if you start the experiment with two different doses, we get two different dosing rates and we get two different steady state concentration. So two different dosing rates and two different steady state concentration. In that case, I will get, if I plot the graph for the same above, if I plot the graph, I will get this one. See here. So I will get this graph. So direct linear plot graph, I will get this graph. What this graph is saying, on x-axis, this side we are taking CSS on x-axis, above we are taking Vmax. Okay. So if you conduct the experiment, this is for the dr1 first dosing rate. Sorry, this is for dr2. This line is for dr1. Okay. So dr2 it is touching here, and dr1 it is touching here. Wherever this line intersect, wherever the line of two dose intersect, extrapolate that line to touch on y-axis, you will get Vmax there. If you extrapolate that line to touch on y-axis, you will get Vmax there. From the intersect, if you extrapolate and touch the line of x-axis, we will get Km value there. As simple as that. Simple. Conduct the experiment in two dosing rate. You will get the two graphs. Wherever the two graphs intersect, extrapolate at y-axis to get Vmax value. Extrapolate at x-axis to get Km value. That how this thing is explained. The next method is graphical method. So what we are doing in the graphical method is we need to rearrange the equation. We are going to rearrange the equation. How we will do that? You take this Km this side, this Km and CSS will be taken the left side. If you take that, you will be left with dr multiplied by Km plus CSS and Vmax. Multiply the dr for the both. So dr multiplied by Km, dr multiplied by CSS and left with the Vmax. Okay. Send this dr Km on right side. If you send them on right side, you will be, here it is in positive side, so here it will be negative side. So you will get this equation if you send that on the right side. Okay. So if you send that on right side, you will be left out with dr by dr into CSS. Send this CSS again on the right side. If you send the CSS, it will go for both. It will divide because it is multiplied at the left side. It will be divided at the both side. In this case, we will cancel CSS and CSS. If you cancel this CSS and CSS, we will be left out with this equation, that is dr is equal to Vmax plus dr Km by CSS. That's how we get this equation. So plot the graph for this equation. Take dr on y-axis, take dr by CSS on x-axis. Dr by this is taken on x-axis, this is taken on y-axis. Okay. In that case, what you will get, because you have negative sign, slope will be negative. The slope will give you Km value and the intersect will give you Vmax value. So non-CSS method is also similar with CSS method. Same method we are following, only thing is we are taking here C, that's all. We are taking that as dr, that's all. Okay, so this is what graphical method. So two methods we saw now. Those two methods are graphical method. Next one is numerical method. So numerical method, how to solve this, how to get that. I don't want to draw the graph. I want to get the value of Km and Vmax by numerically. For that, conduct the experiment with two dosing rates. For two dosing rates, we have two equations for steady state in case of Michaelis-mentate equation. If you conduct the experiment in two dosing rates, you will get two Michaelis-mentate equation for steady state. So this is the first equation, this is the second equation. If you combine both the equation, you will get this equation. If you combine both the equation and rearrange that equation, you will get this equation. In this equation, you are going to find out Km value. You need to substitute what is the value of dr1, dr2, CSS1 and CS2. You will get the value of Km. Once you get the value of Km, substitute this Km value in any one equation. So substitute that Km value in any one equation. You know dr1, you know Km, CSS1. Now you can know what is the value of Vmax. You know the Km by rearranging the above equation. You will know the equation. Okay, by combining both the equation, you get one equation. This is the equation which you got by combining both the equations. From that equation, you are finding the Km value. Substitute the Km value in above two equations. Any one equation, if you substitute the Km value, because you know, if let's say I am substituting in this equation, you know dr1, you know Km, just we find it out. You know what is CSS. What is the left thing there? Only Vmax. We can find what is the value of Vmax from the numerical method. Okay. Now we have some statement here. What is the statement? Is there are several limitations for determination of Km and Vmax, assuming one compartment model, because till now we assumed one compartment model for the determination of value of Km and Vmax. Remember this, one compartment model. Okay, and single capacity limited. So what we assumed here is, while starting the derivation for the equation for the measurement of Km and Vmax, we assume that I am giving the drug and the drug is following one compartment model and the elimination is single capacity limited. So there are many limitations for this process. More complex equations will result and computed Km and Vmax value will usually be larger. Okay, we'll get complex equations and the computed value of Km and Vmax will be larger. When it is larger, if drug is eliminating more than one capacity limited process. If the elimination of drug is more than one capacity limited process, in that case we get complex equation and also will get more values for Km and Vmax. 1. 2. If drug exhibit parallel capacity limited and first order elimination process, then also we'll get this problem. Then if the drug follow multi-compartment model, instead of following one compartment model, drug is following multi-compartment model, then also we'll get complex equations and we get the larger value for the Km and Vmax. Assume if you want to find out if the drug is following which compartment, you need to find out the value of Km and Vmax. Then also you can say that if the value is very large, Km and Vmax, you can say the drug is following multi-compartment or maybe any reason among these three. That's how we are getting the larger K value and Vmax value. If you get that Km and Vmax also for the above thing, so they are have little practical applications for the dose calculations. We don't have that. Okay, so you need to get the Km and Vmax value for only one, for the drug which is following one compartment and elimination is single capacity limited. Okay, so with this I think you understood what I have explained. If you have any doubts, you can message me.